Ni hao. I'm Alejandra González, a Clippy team member that focuses mainly on performance for both the Clippy side of things as well as the Rust diagnostics, so compiler warnings and errors and such. So yeah, Clippy is Rust's official linter, as you probably know. Here are some things about me. So I'm, as I have already said, obsessed with performance, so much in fact, I even proposed it as a project goal twice, maybe thrice, but one got cancelled. So yeah, with great results. I'm a little bit nervous, sorry for that. So yeah, today I'm going to propose a redesign for the incremental system in the Rust compiler. But first of all, let's state the obvious. The Rust compiler is slow, very slow in fact. I've seen people complain that some packages, i.e. Vevi, take an awful lot of time to compile due to, well, the Rust compiler being very complex, which is a side effect of all the positive stuff that we love about the language in itself. Borrow checking takes time, trade solving takes time, macro expansion takes time. As you can see here, there's borrow checking, macro expansion, and trade solving, and I'm there. I paid an artist for that. Everything takes time, and I'm this little fish optimizing a linter in an ocean made of complex technical issues. So I thought to myself, what if we could, somehow, instead of making Clippy faster in single runs, which is something I'll continue to keep doing, obviously, tackle one of these big sharks, so big, in fact, it may even qualify as the fisherman. The incremental system. Today we'll be talking about redesigning it. But first, let's really get down and describe the problem. If you right now go to a terminal and run cargo check and then cargo build, the cargo build will recompile your packages, including dependents, in your local tree, and the target size will be a lot greater than if you just run a cargo build in the first place. It will be the sum of running cargo check and cargo build in both time and target size. This means that if in your CI you run cargo check, then cargo clippy, and then cargo test, you'll be met with redoing the heavy computations that compilers do thrice, making zero use of the existence of the incrementals. So that's why today I'm presenting a conceptual redesign for the incremental system in Rust. This isn't implemented yet, it's just a proposal, but I hope that by next year we have it in the compiler. It's my final objective. So, first we'll go through a quick breakdown of how the Rust compiler works. There are several stages, as in almost any compiler. They broadly are the lexing, which isn't pictured here, the parsing into AST, so more or less the first real stage of the compiler, the here, which is an intermediate representation, the mir, well, the there, a substage of mir, ay carajo. The there, a substage of here, the mir, and then codegen. There are also several substages like linting, macro expansion, borrow checking, or the type inference, all that. Not related, a very useful concept that powers the compiler is the existence of queries. These queries are a special kind of function that saves its inputs and outputs into a query context, like a big database, for later use. So if you run the same query, if you run the query with the same input, it can just return the output without doing expensive computations several times unnecessarily. And even better, these two concepts can be mixed. We can extract each of these compiler stages into their own query. So if the AST doesn't change, the here doesn't get recomputed, the there, the mir, everything can just stay as they are, and we can save lots of time. This is something that more or less already exists on the compiler, and it takes advantage of it. The smart people on the compiler saw that if you queryify the different stages throughout the compilation and you serialize the query context in a sensible manner, it could be possible for us to save all that information in a persistent way for future compilations. And that's how the dependency graph was born. Simplified. Okay, so if we track each executed query and track all the subquery that query calls, we can make a graph out of that. Here we have an example query, which is just as it's just a isEven function. And my query calls my second query with the same key. So the query context saves all that information. So my query depends on, well, my second query depends on my query. And yeah. Which tells more or less okay. Knowing the dependence information between queries tells more or less a complete story of how the compilation went when taken to the compiler stages kind of field. Then we can safely write that dependency graph into a file, and for future compilations, see the hashes and perform the semi-famous try-mark-green algorithm, which goes node by node, checking if the hash is the same as expected, or re-evaluating the query if the original value has changed. So as you can see here, the last compilation, the value was 1, so my query, my second query, they were both evaluated once, but in the current compilation, the value changed to 2. So my query and my second query, they are both recomputed because the original value changed. So now that all that is explained, queries, compiler stages, and we can queryify all that, and the query context, all that, and not important. We know the problem, we know how the compiler works. Here's where we introduce the hero in our story, atomic bits and data dependencies. Let's first talk about what those atomic bits mean. These are little strings, directives, that we tell the compiler that represent what the target of our compilation is. So that means if we just need AST information, so the parsing information, we direct the compiler to only compute the AST and then exit. For example, if all the queries related to processing the AST would be in their own atomic bit. Borrow checking would be its atomic bits. Kind of like leveling what the compiler does into a directive and then having that directive saved along the incremental information. This way, any compiler adjacent activity, such as check, build, or clippy, could declare an atomic level that they'd like to go to. This is the verbose input for Rust-C by a cargo check. In this case, cargo check only needs to go up to borrow check, so we declare it. Here's where for example, while check or clippy go to the borrow checking atomic bit, build goes to the emit bin, so emit binary atomic bit. We can now represent neatly what the last compilation was doing in the incremental directory and avoid tying an incremental to what flags are used or other arbitrary information. And here's where data dependencies come in. Well, we can extract what stage the compiler goes up to via atomic bits. Not all information can be extracted this way, because that's just redoing compiler flags all over again, and it defeats the purpose, and it's kind of useless. For example, the part of the compiler that produces binary files still needs to be re-executed if flags related to compilation change. Like in this case, -C flags, if they change, codegen needs to be counted as to be reevaluated. So this is done via data dependencies. Yeah, they are little bits of information that each query calls and that act like leaves in the dependency graph. Talking about the emitting binary scenario, a data dependency could be things like linking arguments, LTO, or how the symbol mangling should be performed. This allows us to move the change in the try-mark green algorithm from the earlier stage to the necessary one. So LTO options wouldn't impact clippy because clippy doesn't care about what linker you use. Very useful, I know. These data dependencies aren't only for emitting binaries. They are also the values of CFGs for macro expansion, or lint information, or other kind of things. So, apart from not rechecking clippy for linker changes or LTO options, that also goes in the other direction. Build can jump off the progress that cargo check made, because now that codegen options are extracted from hashing, we can guarantee that emit binary will always overlap borrow checking, no matter really what else change, as long as the other data dependencies are still the same. And that's it. That's the great redesign. We have now tackled the fisherman in our odyssey. Users are now insanely happy with how the incremental information is handled, and everyone lived happily ever after. Or did they? We can probably go further. Very little of rebuilds are actually just chaining a cargo build and then cargo check. Let's talk about some other optimizations. If you work on a big project with many dependencies in your workspace, you probably know that emotion when you change something that's ultimately irrelevant, but you still will trigger a full rebuild. For example, adding a unused item or changing a comment or documentation. This sentiment is especially frustrating when you see that in your monorepo you have to build a whole branch of dependencies just because you changed a single constant that actually only affects another branch. So we changed that constant in the earlier slide. It was unused, but as V has many dependents, we actually have to rebuild that whole branch up to root. This is the current model. So rebuild time would be V plus K plus E plus V plus root. Unnecessarily, because we just changed a constant or a documentation or something like that. Maybe even just adding a new line. It's crazy. So, as you may know, data dependencies are not, as you may know, create dependencies are not handled by the Rust compiler itself, but by Cargo. Cargo orchestrates package compilation so that every package has its dependencies ready when it's time to compile it. The process that Cargo follows to check if your if your package needs rebuilding, starts from the outermost dependencies, so from V. Cargo checks if these dependencies have changed in any way, and if so, they are rebuilt. This quote-unquote change means that cargo, apart from checking obvious things like the compiler version of if the file contents have changed, also checks for more innocuous properties such as last modified time or LTO flags for cargo check or other sometimes useless information. So here's where the second key concept of the talk comes in. In fact, it's the third. Two-stage fingerprints. Instead of compiling all the way to emitting binaries, we only go as far as to perform name resolution. So what's name resolution? I hear you ask. Name resolution is the stage in which the compiler actually finds what you're talking about when you mention items or variables in your source code. So in this case, we have a function foo and a function main. Name resolution is the stage of the compiler that actually, when you call the function foo, figures out what foo in that context means. It takes into account variable shadowing, modules that haven't been imported yet, and obviously every single item in the given module. So as you can see, it generates definitions ID or def IDs. Being that definitions IDs are calculated on name resolution, we need to see if those hashes that were changed in the dependency were used in the dependent. So the problem at hand now is to come up with a way to know if K in our crate tree depends on one of the modified items on V, even indirectly. So yeah, there are lots of ways to do this. The first way would be to calculate the two modules up to name resolution in parallel, and then compare if the dependent module needed any of the def IDs that were changed in the dependency. So we go up to name resolution in both modules. The required def IDs are A, B, C, D, and in K, and in B, it's changed V, W, and X. We can see here. And if there's no overlap, there would be no recompilation because it's just not needed. In this model, we take advantage of the fact that the dependent module would have to be rebuilt either way in the old model. So we're saving the process of type checking, borrow checking, and code generation, which takes a huge part of the compilation process. Another way to solve this conundrum is to track the relationships between all items in the incremental of the dependency. In the previous compilation. And write those to a file. And just check that file before recompiling the dependency. This saves even the parsing state of the dependent because we already have all the name resolution from the previous compilation. And you might be thinking, how will cargo signal to the compiler to just go up to name resolution? Yeah, you're correct. Atomic bits, everything is intertwined. It's all a central theory and Santa's real. So that third key concept, the two-stage fingerprint verification, is just an example of what atomic bits can do. And similar to these ideas I've been given, the powerful concept of atomic bits has lots of unexplored potential. I have a paper right here. It's this one. With some of them, I've managed to come up with some optimizations. So yeah, that's more or less it. Thanks for coming here and listening to my talk. You can reach me at any point in the event or via the internet. I sadly forgot to put my email in the final slide. But yeah, thanks and have a great day.
Thank you, speaker. We have time for one question.